Thank you very much for the nice introduction, Nico. It's really amazing to see such a crowd on Sunday morning. I had a exhausting week, I can say. I mean, probably being a local, you get invited to many parties, and then also you have to organize too many. And it's still very good to see all of you. Uh, I wanted to talk about my journey into the field of Earth observation, coming from a computer science background, and it was meant to be lightweight talk for a Sunday morning, but we had an excellent keynote on the topic by Christian Eagle uh, on Tuesday at the LS Unconference workshop, and then yesterday at the AI for Climate and Conservation, we had a another excellent keynote by Philippe CS on the same topic. And there's only so many tree-related talks one can take in those 6 days, right? So what I did was I said, okay, I'm gonna give you a very brief overview of my journey, but then we are gonna talk about something more closely related to this particular workshop, more closely related to representation learning. And in the end, I'll end with some of the fun projects that I've been involved in. So it's going to be a lot more lightweight talk, I hope, compared to the last one, for example. So let's dive in. Uh, okay, but I click on it and it goes away.
Once you
Ah,
click, you can just use the
yes,
exact.
perfect. Thanks a lot. It was not clicking. Sorry. Yes. So, uh, yeah. So what I wanted to present initially was like how I actually got started into the field of Earth observation, and that started with mapping trees at very large scale. And one of the most influential works that I've been involved in is mapping individual trees over scale in Northern Africa. We mapped all the trees in that area that you see up north, and we also calculated biomass using allometry. The nice thing about this, you can then look at plot levels, see how, for example, the things have evolved over time. So you can see like how the tree ecosystem has evolved. So this is an example from a plantation in Senegal, and you can see how trees grew in 20 years in that particular plantation. Here we mapped individual trees, and the tree crown was then converted to biomass using allometric equation. I think Christian presented it very nicely on Monday. Several of you I can recognize in the room were there. So for the in the interest of keeping things interesting, I will skip over it. And we have done something very similar for various parts of the world. We have done something very similar for Rwanda, for Denmark, and lately for India. What's particularly interesting about this one project that I've been involved in, and I'm clicking over things like in 5 seconds, but just to clarify, these all projects are multi-year work of several people, and it's very nice to look at a map and then click over it, but that does not mean you get it in seconds. So it's a huge amount of work, very nice, thorough works. But in the interest of what I want to present, I'll skip over it a bit. So this one, yes. So we studied decline in trees in farmland in India, and one of the very interesting things we did here is that we built a high resolution satellite image mosaics over approximately 12 years, and then we traced the trees in this period. And we could see that over this decade, a vast majority of large trees died out. And the reason why I want to especially mention this particular project is this is to highlight what happens when you do these kind of studies. So we published this paper back in May 2024, and almost immediately afterwards, it was picked up by the National Green Tribune. It's essentially a body in India that's responsible for maintaining um, the ecosystem, the cultural heritage we have. And they picked it up and they filed a case against the government. So suo motu means taking on their own accord. So they took up the matter on their own accord without somebody having to complain that, hey, these many trees have been killed or died in the last years. And they did that on their own accord, and this shows, for example, when we apply the methods we are developing here at scale with rigor over large areas, over large time scale, it can really have impact, because once you have a case like that, then of course the government is suddenly now responsible for making sure that the situation is amended in the future, it's corrected for. And my colleagues at TreeSense, they have been doing a super excellent job in mapping individual trees, and they have like made huge strides in the process in the last years. In some sense, it's very easy to explain what they're doing. They take high resolution satellite imagery, which is typically 3 meters or higher, so very often sub-meter. But even if you have 1 or 2 meter or 3 meters, it's pretty good. And you apply some kind of a deep learning model on top, and then you get your prediction, which could be a tree crown, which could be a tree center, which could be something related to it. And my colleagues at geography department particularly have been doing an excellent job in extending these approaches over large scales. And this is, for example, a snapshot of the work we have already published on Google Earth Engine. And you can look at individual trees over very large areas with this. I know that most of the people here are already very good with deep learning, but there's one thing I would like to point. What is the secret sauce here? Like, why how we have been able to basically scale up tree monitoring to such large areas with relatively simple methods? And the secret sauce is simply this approach. So I think we have over the years tried various ways of how do you define a tree. Okay, if you talk to ecologists, the kind of data you get from ecologists from the field is like, here's the location, here is the diameter along the maximum 2 points of the tree, and this is the orthogonal diameter. So they represent typically either a tree as a circle or as an oval, and then you get the two axes mapped. So this is what you get from ecologists, right? But if you're in the image domain, then you say, hey, how about I draw a polygon around it? And I say, hey, this is what my tree looks like in my image. So I now have a polygon. So you can have a polygon, you can do segmentation. You can also do a box around it, which is actually approximation of some sort. You can do point detection. You can say my tree is located here. This is, for example, anchor-based approaches are also very good. You can do a simple heat map, which means nothing that except that you have a point approach with some distribution around. So you have a Gaussian around a point. But I think what really stands out is this particular approach, where what you do is you say, my tree is a point and some distribution around it. And now if you can predict both the point and how big it is, you suddenly have almost everything you need to map the upper canopy. And this is pretty amazing because it's highly scalable. Like a polygon like this would have typically few hundred points. That means few hundred clicks. And a thing like this is a single click. So from a practitioner's point of view, if you can get essentially the area with a single click instead of doing 100 clicks, it really scales. And I'm not kidding. Several of my colleagues, they have literally created labels of 5 million trees by clicking over the years. So if they would be doing polygon, which is what I initially recommended them to do when they started with, they'll be still in like thousands domain. So yes, the secret sauce of having a coverage like this over very large scale is honestly efficiency. And having worked with mapping trees over the years, I can tell you that this is probably the most efficient approach. My colleague Dimitri Gominsky has done an excellent job in this regard, and he has an archive paper out recently called Trees as Gaussians, Large-Scale Individual Tree Mapping, which describes many other things, but also this approach in more detail. So if you are interested in it, please check it out. So So this is my essentially how I got into tree mapping, and this is what how I view it now. And I think this recommendation is also valid for many other mapping projects. That how do we actually make sure that the practitioners are able to do their job efficiently? And in that particular case, it's very important that you find an approach which is efficient, which is scalable, and which people can adopt rapidly. Okay, now so now let's talk about something more related to the topic of the workshop, which is foundation models for Earth observation. And I would now like to present uh, a work which is a brainchild of Nico Lang, who's sitting over there, who just introduced me, which was spearheaded by Vishal on MMEarth, exploring multimodal pre-tech tasks for geospatial representation learning. And I think most of us know, but let's again revise. Why do we actually care about EO foundation models? And there are several reasons. Like we often have limited amount of reference data in the field. The reference data we get is very biased, and it can be very difficult to collect more data. So this applies to various data sets that are out there. If you have just a visual look, you can see how biased those data sets are. At the same time, we have this very nice opportunity that we have few hundred, I actually don't know the exact number, I should have looked it up, like at least few hundred satellites out there, which are all looking at the same thing. They have different spatial resolution, different spectral resolution, different temporal resolution, and different radiometric resolution. So those are the four resolutions you talk about in remote sensing. But at the end of the day, they're looking at the same thing. They're looking at the same planet. And that allows us to basically align all of that data automatically. And that's a super powerful thing. So just having a paired view on thing is a very unique characteristic of the field we are in. And I think I truly think this is what makes Earth observation the special field, and this is why Earth observation has a special like place in the machine learning community, because I don't think it's possible to get that much aligned data from different modalities as we have in Earth observation. So what we did was we exploited that. We created a global multi-model pre-training dataset. In MMEarth, we collected 1.2 million locations, which is roughly the same size as ImageNet. The data came from 4 years, from 2017 to 2020. You can see the distribution over the months. We collected 128 by 128 pixel tiles, and from Sentinel-2. And at the same time, we aligned 12 modalities with it. So different products, sensor maps, and climate data, for example. The products that we used could be divided into pixel level and image level. At pixel level, we had Sentinel-2, Sentinel-1, digital elevation map, canopy height model, dynamic world, and ESA world cover, which are essentially maps at the same resolution as Sentinel, aligned with the Sentinel data. And we had image level information such as the biome, ecoregion, temperature, mean, minimum, maximum, precipitation, geolocation, date, including the cyclic encoding of the month. And with that, so why did we do that? So why did we also want to have image level modalities along with the pixel level modalities? Very often what you have is, for example, if you're in the desert biome, your pixel level modalities have almost no information. It's too plain. So it's very hard for a model to learn from such a thing. And this is where we think the image level modalities can be very useful. Because then you may have more information in your precipitation, in your temperature, and biome, for example. So this is an image from Saudi Arabia. But if you then look at an image from Ecuador, you'll see that the image level modalities are also the pixel level modalities are of course very powerful. So you have a lot of variance in there, which you can try to learn with the model. So this is what we did. What we wanted to do is we want to figure out how do multi-model pretext tasks impact representations. So what we did was we took the Sentinel-2 image as input, passed it through a encoder, got the embeddings out, and we used the mask autoencoding, the manifold learning approach. So essentially, we were masking out 70% of our image. 70%, right, Nico? 70%. Yeah. We should have looked it up. 70% of the image, uh, and then encoding it just like any MAE approach. And from that encoding, we were now reconstructing the original image as well as other pixel level modalities and uh, several image level modalities. And important thing to note here is that there's a different decoder for each modality. So we had one typically very, very small decoder, just a few thousand learnable parameters for each modality. So we did that on our pre-training dataset. Yes, and the idea is that now you can use the pre-trained encoder for your downstream tasks. To evaluate our model, we used GeoBench, which was the state of the art back then when we were doing the project. I think most of you know what GeoBench is, but it includes things like BiggerNet, which is thanks to Bigam, and SO SO2 SAT, Eurosat, Cashew, and several. So there are many classification, segmentation, multi-label, multi-class problems in there. So as any curious person, the first thing what we want to know is like whether does it actually make sense to do any special thing for the Earth observation data. So what we did was we evaluated how do ImageNet weights work or compare on these tasks. So we took a model. So we're using a Connext, very small one, Eto model. And we took that model trained on ImageNet and see how does it perform on these particular GeoBench tasks in limited data regimes. So if your training set size is 1% of the data, or 5%, or 50%, or 100%, how does a pre-trained model trained on ImageNet performs? So we did that, and then we could compare that with what happens now if we use Sentinel-2 data instead of ImageNet to do the same things. And we see that just by training it on Sentinel data now instead of ImageNet, we get some improvements. It's not too big in low data regimes, but there's still some improvement. But now, if you add multi-model pretext tasks, it particularly improves the representation in low data scenarios. So this was a very interesting finding we had that by forcing the model to predict these multiple modalities, we could actually perform better in low data regimes. We also compared our model with some of the other models which are particularly suited for Sentinel-2. So we did not compare it to every other foundation model out there, but only the ones particularly suited for Sentinel-2. And we had a very small model. So Convex V2 Eto, 3.7 million parameter. And we saw that our very, very small model actually performed quite favorably compared to the works we were comparing them against. And the next obvious question we had is, do we actually need 1.2 million data samples? So the reason why we chose 1.2 million is, as I said, we want to be comparable to ImageNet. So do we actually need ImageNet level data or ImageNet size data? So we then compared it. So we then created a subset of our data set, 100K, and then compared the performance. And there was a clear decrease or clear reduction in performance if you had only 100,000 samples. But now if instead of going with 112 versus 112 patches, if you now decrease the patch size to 56, there was actually no difference in performance. So it was very, very similar. So what we found is that fewer locations deteriorated the performance, but smaller images works equally well. Just to know here for MM64, we had to also reduce the masking in the same proportion. So this is one thing you have to do to make sure that it also works with the smaller image patches. For the last bit, I want to talk about why are we doing it? What's the fun in Earth observation? So I could have included many different projects here, but I chose the ones which I think are rather, uh, rather interesting, rather, is they're basically we're doing it just to satisfy our curiosity than anything else. So one of these projects is mapping cows from space, so space cows, and uh, this is work mostly done by Venkana, who is sitting up there, and we were contacted by some of our colleagues, and who said, in the dryland regions, what happens is that the cows they gather around boreholes, so they have places where they actually where the cows come to drink water. These things are called boreholes, and during the dry season, basically all the cows from the region come to the boreholes to drink water, and this is one of the boreholes that you can see. It's next to a village. Okay, there's a borehole here, and the white dots that you see over there are cows. So they're coming there to drink water. And in this project, we are interested in essentially mapping and doing a census on the cow population coming to these boreholes over a large time period. So it's a very difficult task because if you look close up, this is how cows look. But even in 50 centimeter resolution images from Worldview, so this is a collection of images from Worldview 1, Worldview 2, Worldview 3, and GeoEye-2 satellites, Maxa satellite. But even these very, very high resolution satellites, the cows are barely 3 or 4 pixels big. So mapping objects that are so small is a challenging task. Venkana had a nice, a clever trick to map such small objects in his model architecture, and even for humans, it's very difficult to do that. So if we had multiple annotators annotating the same objects, and then we also compared how does our mapping perform against human annotations, and they were much closer to expert annotation than a random annotation in this particular case. So that was one of them. The other one is mapping of ancient dry stone monuments in Sahara. So the thing is, Sahara used to be green not that long ago. So if you go back only 10,000 or so years, there used to be much more vegetation in Sahara. The Lake Chad, which is quite small in the moment, used to be super big. For example, this one. Compared to what it was in the past, it used to be really, really big. And there were lot more water, vegetation in the area 10,000 years ago. What that also meant was there were a lot of people living there in those areas. And the populations there had their own unique cultures. Okay. And what we are doing in this particular project is we are mapping the dry stone monuments. So the monuments built with rocks, essentially, that are spread over the whole Sahara. There are approximately 60 types of monuments defined in the archaeological literature in this region. Super nice thing is, because it's a desert now, there's not so much activity compared to some of the other parts of the world here. So what that means is that these monuments are still visible. They're degrading, they're deteriorating, but the rate at which they're deteriorating, it's significantly slower than in other parts of the world. So like they're also, for example, monuments in Greenland, and they are uncovering as the ice sheets move. But their deterioration rate is so fast that if you don't manage to map them and then preserve them within less than a decade, actually, they'll go away because of how rapid the environment changes. But luckily, Sahara is rather unique in that sense. One particular monument that we're interested in is called a keyhole monument. The reason why it's called a keyhole monument because it looks like a keyhole. So, you can put your key in and then open, and that's why it's called a keyhole. The key characteristic of a keyhole is that you have a outer ring, outer shell, then you have an inner ring, a tumulus in the middle. So this is the tumulus, and then a corridor, and it's elongated, and the corridor almost always points to east. So the variation in this in the keyholes is less than 15 degrees. So you can actually, and our hypothesis is that you can trace back at which point of the year the keyhole was built by looking at where it is pointing, because uh, during the whole year the where the sun rises changes, and you can actually trace that back. So that's what we think. So that's why there's a tiny bit of variation, but it's almost always pointing to east. So it's rather it's a fascinating structure. On the ground, they can be up to 180 meters long. So the longest keyhole is 180 meters, which is really big if you think about it. And they are just collection of stones. So built with just stone. They are funeral monuments. So that means typically, not always, but typically in the tumulus in the middle, the tumulus in the middle was used for some. So you'll find some dead bodies, and it was used as a funeral monument. Yeah, the last thing is they are approximately 2 to 6,000 year old. So there's a large time period over which they were built. Okay, this is this is how they can look like, and our goal is to basically find them. So the one above is not a keyhole. That's a tumulus on a platform. That's a completely different type of monument. This is also not a keyhole. This is also a tumulus on a platform, but that is a keyhole. But we are actually looking for many different types of monument. Keyhole is one of the most significant ones that we are looking for. And we did the study. We mapped them over whole of Sahara. And if you use deep learning, then the good thing is you can scale up mapping really fast. So I can say that we found the southernmost keyhole, the easternmost keyhole, and the westernmost keyhole when we did our study. So the northernmost keyhole is still the one that was already in the literature. So we can now actually create a complete map of keyhole monuments. And now you must be wondering, like, there's so many things to do. Why is somebody interested in mapping how somebody structured some rocks 3 to 6,000 years ago? And there's a very important reason for that. The monuments, which are 60 plus in this region, 60 types of monuments, that's what I mean. They're it's estimated there are over 2 million monuments in this region. So huge amount. But what's super interesting is the people who lived back in the days, you can trace back their lineages now in the society that are living in this region. So there's a linkage between the languages that are spoken in this area and how some of these monuments are distributed. So, and this is also why we are very interested in how far does it go, because that tells you how far did that particular ethnic group, for example, traveled back in the days. So by studying these monuments, you can understand what was happening back in time in these societies and how that has influenced the language development that has happened in the region, for example. There are also various similarities and dissimilarities in, for example, the dietary pattern that these populations followed. Some of them, for example, relied on fishing. Many other populations did not. So by looking at that, you can understand some of the current cultural phenomena that are in this area. This is the second last slide. I would like to say that we can also do something more useful sometimes. And this is, for example, to map artery craters in Ukraine of this terrible war that Russia has launched. And I think at some point, Russia will be held accountable. I strongly believe that. And I hope that our work will contribute to that, because we map all the craters and we can show that we can estimate also how many of them are unexploded based upon our work. With that, I would like to thank you for your time, all my super nice collaborators for all the amazing works that we have been doing over the years. And thank you very much.